Good afternoon, everyone. Thank you to attend my talk. Today, I'm very honored to be here and share my ideas with all of you. My name is Nicola del Gobbo, and I'm a developer at Pacli. In my everyday work, I take care of building Pacli backend systems, and for most part, I use Node.js, sometimes C++. In my spare time, I try to give my contribution to all frameworks, modules, libraries that I use in my work, and obviously, I like creating a new one. Today, the talk is focused on Node.js native add-on and start with its definition. In a very simple way, native add-ons could be considered as C++ code called from JavaScript. They are a bridge between our application programming language JavaScript and the native environment that is completely written in C++. And yes, you can call C++ function methods directly from JavaScript. If we take a look at the Node.js documentation under add-on section, Node.js add-on are defined as dynamically linked shared objects written in C++. And you can use it through function require and use it as any other JavaScript module. This is very important for developer experience. In this case, I'm talking about developers that use native add-ons, because for maintainers is another story. How is it possible? All the magic is behind the Node.js architecture. Node.js is built on some C++ libraries. Between them, the most important for us as a native add-on developer are Wait and libuv. Wait is a JavaScript engine that takes care to compile JavaScript code, execute it, and through its API, we can create object, function, and do almost everything that we do on JavaScript side. libuv is a high-performance event.io C library and has the responsibility to handle the event loop, our main thread, and all asynchronous I/O. We will use libuv API to create asynchronous function. Why should we implement a new native add-on? The first reason is for performance. In general, C++ code performs better than JavaScript code. But it's really true if we think about that CPU-bound operation like image processing, video processing, compression, scientific calculus, and all algorithms that at one point execute some CPU-heavy tasks. If you create a native add-on in these scenarios, you will gain more advantages in performance. Sometimes you just want to integrate some legacy application. So you have an old C++ code, and you want to expose some of its functionality through your new Node application. The right choice is to create a native add-on and call your old software directly from JavaScript. Time to time, you don't find what fits your specific needs on NPM. Yes, this happens. And you have to take a choice, implementing your solution entirely on JavaScript. But if we think about libraries like ImageMagick, GhostScript, FFmpeg, TensorFlow, it's an insane idea. Rewrite these libraries completely in JavaScript. Because at the end, you have to concentrate on business logic of your application and not on developing a single module. So here, the right solution is to create a native add-on. And to do that, you will spend maybe 1 to 2 weeks. All depends on your knowledge about native environment and C++. But for sure, you will increase the probabilities to deliver your software in time. Node is used even if to create a desktop application, maybe using Electron, Node WebKit. In these cases, you won't use all the underlying resources in terms of CPU and GPU to execute the most complex task. You will get two benefits, a better performance local side and a better performance on the server, because you will call the server only for data synchronization. The last reason to create a native add-on is to get a better error handling. You don't have to parse some string to identify if there was an error or maybe what kind of error just happened. Even if you are integrating an old C++ library, you will get an error code that explains the error. Maybe you are integrating a modern C++ library and you can use the exception to intercept the error. Until now, we understood that native add-on give us great power, but from great power comes great responsibility. I'm saying that because there are some problems in implementing native add-on, and you have to take a choice to handle them. The first problem is the Fragmentation Api. The API to implement native add-ons have been changed across different versions of Node.js, and the most changes were on Vue8 API and the Object Wrap API. So at one point, we need some kind of adapter that help us to stay compatible across different versions of Node.js. We have this adapter. Its name is NaN, Native Abstraction for Node.js. It guarantees the API compatibility, but remains some problems. NaN is a thin layer built on Vue8 API, so it's strong bonded with Vue8. What I mean that it's not JavaScript engine agnostic. So you have to recompile your native add-ons when you switch to a different Node.js version. This is okay on a development environment, but it's a source of many disks on a production environment. At one point, your code have to compile on different platform, different architecture, different compiler. What I mean here is that it's not an easy task to write portable C++ code. The last problem is in documentation. Maybe you have to integrate a poor documented C++ library, and the only choice you have is to go inside the source code and try to find what you need. Out there are many good references about Node.js native add-ons, but there is a lack of materials or resources that explain the most difficult concept about native add-ons development. So here, if you want to learn the most advanced technique, the only possibility is to take a look at code written by other developers. When I start to build a new native add-on, usually I use this boilerplate. Here, the most important elements are the src folder that contains all the C++ code and maybe your native dependencies. The lib folder contains your JavaScript code. We have the usual package.json and a new file called binding.zip. Here, there are all the building configurations that Node.js will use to compile and build your native add-on. At the end, your module will be composed by two parts, one written in C++ and another written in JavaScript. And the JavaScript part will use the C++ part to expose some features. Here, I reported a portion of code extracted from bcrypt. Bcrypt is a module that helps us to hash password. This is the JavaScript part, and we import the add-on and use some of its function to create a new function. Just it's very simple. Use the native add-on. Just import it and use the function that it exports. Here, just a note about a package.json file. If you want that npm will build the add-on automatically, you have to set the zip file to true. To understand how to create this function that native add-on export, we have to take a look at C++ part. All start from the registration and initialization. Here, the node module macro creates all the necessary code to register our module with specified name. In this case, bcrypt_lib. When the add-on will be requested, the node module will ensure that the init function will be called. And on the init function, we export our functions object, all we need. Here, in the example, I signed gen so sing, and all the native code responsible for this function is generate so sing. What happened in this method? As the first step, we validate our input. Remember, on the native side, you have all the necessary methods to validate your types and data. Don't waste your time on creating on the JavaScript side code that try to identify what types you are passing to native side. After this step, we pass all the data from JavaScript context to C++ context. And we will use this data to execute some elaboration. After that, we return the data to the JavaScript context. The most important concept here is that when we pass data from C++ context to from JavaScript context to C++ context, this data will be copied. Because the JavaScript data are immutable and are managed by void. This is the most straightforward pattern that you can use to create a native add-on. It's used because it's simple, and you can use your C++ code without modification. In fact, there is a high decoupling from the JavaScript side and the C++ side. Just a note about bind.zip. Here, the most important parameter is a target underscore name that have to be set at the same value you used on the node module macro. This is a very simple example of a bind.zip file. Sometimes finding the right settings is very difficult. So refer to zip documentation, but for me, most useful is a Node.js wiki, where you can find a list of binding zip file written by other developers. We can categorize our native add-on based on the amount of processing time spent on C++ code and the amount of data flowing between C++ and JavaScript. If you are on the right quadrant, you can create asynchronous add-on. These mean that all the computation happen on the event loop. If you are on the right quadrant, you have to create a synchronous add-on. In this case, all the JavaScript code return immediately, but just before we pass our data to a worker thread managed by libuv, and all the computation will happen out of our event loop. So most often developers consider only differences between right and left quadrants. But the differences between top and bottom quadrants are important because they consider the cost of copying of data. If you are transferring a big quantity of data from C++ to JavaScript and vice versa, you kills all the performance benefit obtained using C++, copying the data. So here the right solution is to use buffer. Buffer are special JavaScript objects that use the memory out of the weight heap. So you can access it directly from C++ without copy this kind of data. Here I reported an example of an asynchronous function. This example came from code of GoScript4.js, and the execute function take as input a callback and a string. The string represents a GoScript command, and the function returns immediately. But just before, we pass all the control at worker thread managed by the BUV. We accomplish this task calling a sync worker and pass to it an async worker. It's very simple, and create an async worker is very simple too. You have to extend async worker class and implement two methods. Execute method, that is the method that will be executed on the worker thread, and the handle k callback, that is a method that will be called after the execution. So in this method, we'll reassemble our data and pass calling a callback to the JavaScript context. Here, there is an example of a buffer usage. In particular, we are returning a buffer to the JavaScript context. Remember, buffer are objects that use memory out of weight, but they are under weight controls. So when weight destroys the buffer, we need some way to destroy the memory, to free the memory that the buffer use. We have to set a callback that has this responsibility. But sometimes you are integrating some C++ library that free the memory internally. So you cannot do anything, and the only solution is to copy the buffer from native side to JavaScript side. It's inefficient, but it's the only choice you have. Sometimes you won't expose your C++ code directly on to JavaScript. To do that, you have to extend the object wrap class that has all the plumbing to connect your C++ code and JavaScript code. All the classes that extending object wrap can be instantiated from JavaScript using a new operator. And their methods can be called directly from JavaScript. But the word wrap is only refers to a way to group your methods and your state. But at the end, it's your responsibility to write a custom bridge with your C++ class methods. Here I reported an example of usage of Object Wrap API, and we have an initialization code where we are creating a function. We set the name for this function, and its prototype methods, the assessor methods. Update the constructor because in using this pattern, we need a persistent reference to a constructor because we need to access it out of the initialization code. Then we have the implementation of one of the method that we have set on the initialization code. Just for a recap, what I learned from my experience on implementing native add-ons, try to stay simple. Create a very simple interface between C, C++, and JavaScript. And if you want to insert complexity, do on the JavaScript side. And yes, think carefully to your JavaScript API, because at the end, you can change your native code, even if your native dependencies, for many reasons, maybe for performance, because you find a C++ library that perform better, but change your JavaScript API is always bad, because developers that are using your module will be in a very difficult time. Use Object Wrap API to expose all your C++ code directly to JavaScript. Don't waste your time to create functions to validate types. You are on C++ environment. You have all the methods to do that on the native side. Even if you are integrating a rich C++ library, expose only what you need. And if you want to use your native add-on on a distributed system, create asynchronous function. If you pass big quantity of data between C++ and JavaScript, consider the use of the buffer. And if you have many parameters, JSON could be the right solution. And if you want more performance, consider the using of the protobuf. That is about 5-6 times more performant than JSON. Today, the largest number of native add-ons are written with NaN. NaN helps us to stay compatible with all the versions of Node.js. I think that today, if you want to implement a native add-on and use it on production, you have to use NaN. But there is the new NaN API that, for me, will be a game changer on native add-on development, because it guarantees the API compatibility, allows us to use new ES6 types. It's really isolated from V8 API. We have 2 implementations, one written in C++ and one in C. So for today, I prepared a repository that contains some demo that use all the techniques that I discussed. If you want to talk about that, we can do after the talk. I'm available. And for now, it's all. I say thank you for your attention.